In this video, I'm going to take you through two concepts in chapter 7, which is about equilibrium. Okay, so I would have given you an additional handout in class and you should refer to it. Okay, so basically what happens is that we have a horizontal rod, okay, and we have two weighing scales here, A and B, which the reading which you don't know, but you know that you are able to take the readings in class. Okay, we will see the actual readings in class, but in this video what's going to happen is that we are going to hang a 10 Newton load here. Okay, that's 40 cm from scale A. So how do we actually predict the readings on scale A and scale B? Okay, so what happens is that we can use this idea called the principle of moments. A moment is of a force, is just the force times its perpendicular distance to one point, yeah? Okay, and the principle of moment says that a clockwise moment equals an anti-clockwise moment. Okay, so what do we know about a clockwise moment and anti-clockwise moment? Okay, so for example, let me show you what is a clockwise moment. Okay, so this, let's say it's a rod, and this is my pivot, and this is my force. My force and my perpendicular distance is E. Okay, so my moment is equals to force times distance, and because you notice that the force is downwards and the pivot is here, so the rod will tend to go this way, and of course in this case this is a clockwise moment, right? And but if we change the direction of the force, so for example the pivot is where on the left, and if our force goes upwards, then we know that again our moment is force times distance. Okay, but in this case the force will tend to bring the rod up, okay, and the rod will rotate this way, so this is an anti-clockwise moment. Okay, so here we go. Right, so we have enough theory to actually predict the readings on the scale. So here we go. So for example, there are two scales here, A and B, right? So let's pretend that we fix a pivot at scale A. Okay, so remember what we can do is we can fix our pivot anywhere. So we can fix our pivot at scale A. So our 10 Newton is here. Okay, and our scale B is here. Okay, so 10 Newtons and 40 cm. Okay, so let's write down so our clockwise moment. Okay, in this case it's 10 Newton times 40 cm, because notice that if I were to 10 Newtons would pull the rod downwards in the direction of the clock, yeah? So that is a clockwise moment, so 10 Newtons times 40 cm. Okay, that's my clockwise moment. Now, we are now ready to see that B gives us an anti-clockwise moment. Okay, this is 100 cm. Because if for B, it goes upwards, yeah? Okay, and for B it goes upwards, so it's in the opposite direction to the clock, and therefore it is anti-clockwise, yeah? Okay, anti-clockwise. Okay, moment, no space. Okay, anti-clockwise moment. So for B, we don't know B, right? So let's just leave B. And the distance from B to the pivot here is 100 cm. 100 cm. Okay, so clockwise moment equals anti-clockwise moment. We are able to solve for B. So let's B is 10 Newton 40 cm divided by 100 cm, or is equals to 4 newtons. Okay, so that's the value for B. Right. Okay, so let's apply the principle of moments for the calculation of A. Okay, so in the next slide. Right, so I've already discovered that B is 4 newtons. So now in this case, we actually don't need to find B. So now we can repeat the calculation by now putting a pivot at B. Okay, so this is my rod again. Right, so let me color the rod here. So this is my rod. Okay, now I put my pivot at B. Now this is 10 newtons. And now my 10 newtons is how far from our pivot at B? It is 60 cm. Okay, and my A is now 100 cm. Okay, so now again, let's look for the clockwise moment. Okay, now that I've changed my pivot, right, the force that gives me the clockwise moment will change as well. So therefore, you see that A goes upwards, and if the pivot is here, you notice that it tends to turn in this direction. So therefore, it's in the same direction as the clock. Okay, so my clockwise moment is now A times 10,000 cm. Okay, so always know where your pivot is. Okay, so now my pivot is here, my 10 Newton force is here, and if I were to have a 10 Newton force with respect to this pivot, then you notice that the rod will tend to turn in the opposite direction or in this direction, right? Okay, which is anti-clockwise. Okay, anti-clockwise moment. Okay, so therefore this will be 10 newtons, okay, times 60 cm. Right, okay, so here we go. So now we are ready. Okay, I have no space below, so I'm going to write at the side. So we are ready to say that A equals to 10 newtons times 60 cm divided by 100 cm. Okay, is equals to 6 newtons. Okay, yeah, so we have used the principle of moments in this example by putting our pivot at B, okay, and finding the reading of the scale at A. Okay, so now what happens is we have one last check to make. So we've discovered that this is 6 newtons, this is 4 newtons. So we only have to check that the sum of forces is 0. So if we take upward force as positive, so we have 6 newton plus 4 newton, and my downward force is negative, so plus into minus 10 newtons. This is equals to 0. Okay, so in this case, the sum of forces is indeed equals to 0. Okay, so what's happening here? Okay, so you notice that it is in equilibrium because I have taught you before that the sum of forces is equal to 0. Now, it turns out that for equilibrium, okay, on top of sum of forces equals to 0, it can also happen at the clockwise moments, which equals to anti-clockwise moments. So therefore, there are two conditions for equilibrium. One is that sum of forces is still 0, and two, the clockwise moments must equal to anti-clockwise moments. And both conditions must be met in order for you to declare that an object is in equilibrium. Okay, so this is the end of the video on equilibrium.